So I have two expressions here, 1 over root 2 and root 2 over 2. They're both equivalent expressions, so if you did them on your calculators, they would both come out to about 0.71. But my question for you is, which one's simpler? If we could have either one of them, which one would be better? So let's think about it this way. Root 2 is approximately equal to 1.4. So this expression is sort of like saying 1 over 1.4. The second one, root 2 again is 1.4. So this is like saying approximately 1.4 divided by 2. Which one of these is easier to visualize now? I don't know about you, but I don't really know how to do 1 divided by 1.4 in my head. Really, I have no idea. If I had to try to figure that out, I really wouldn't know where to start. The second one, however, 1.4 divided by 2, that's sort of like saying 14 divided by 2. So I know that's going to be approximately equal to 0.7. Now which one's simpler? Well, obviously the second one was easier to calculate in my head. And if you look at the reason why, look at what's in the denominator of each one. The first expression has a root 2 in the denominator, and root 2 is an irrational number. Irrational numbers obviously never terminate, never repeat. And in the second one, I have 2 in the denominator. 2 is a lot easier to picture. It is a rational number. It can be expressed as a fraction. And I know how to divide by 2. That's something I'm used to doing. So really, if we had an option between using the first or the second term, this term or this term, really the one that makes more sense is to use this one. So in this course, when we get to our final answers, we're going to want to have something that looks like that. Now in this lesson, what we're going to do is the process of going from this first expression to this second expression. And that's called rationalizing the denominator. So let's do an example. How can we rationalize the denominator down here in this question, 4 over root 3? See how there's the root 3 in the denominator? We don't want that there. We want to somehow get rid of that. So how do we do that? Well, the trick is you want to turn what's in the bottom into a perfect square, right? If we take the square root of a perfect square, we know we're going to get a whole number. So we can turn 3 into a perfect square by multiplying it by itself, right? And we can always do that to create a perfect square. So what we're basically going to do is we're going to multiply what's in the bottom by the square root of 3. So now you'll see if we multiply that 3 by that 3 here, we're going to get 9, and then the square root of 9 is 3. We can do that. But we can't just multiply the denominator by 3. We have to also multiply the numerator by 3. And the reason we're allowed to do this in math is because we're basically multiplying by 1. Root 3 over root 3 is just equal to 1, right? So we haven't really changed the value of this expression. We've just multiplied it by 1. So now we can simplify. 4 times root 3 is just going to be 4 root 3. And root 3 times root 3 is root 9. Simplify a little bit more. We can't really simplify what's in the numerator anymore. 4 root 3 over, and root 9 we know is just 3. There we go. Look what's in the denominator. We have rationalized the denominator. We haven't changed the value of the expression. We've just made what's in the bottom rational. And we always like to express our answers with a rational denominator. Let's do one more of those. 6 over 5 root 2. Think about it. What are we going to multiply the denominator by and the numerator by in order to get rid of that root 2 in the denominator? The answer is root 2. And again, we have to do it in the denominator or the numerator. Let's simplify 6 root 2. And in the denominator, remember we multiply the things that are underneath the radical sign. So 5 root 4, which just ends up being 6 root 2 over 5 times 2. Root 4 is just 2, so 10. And then we ask ourselves, can we simplify this anymore? And the answer is, yeah, we can reduce the fraction, right? 6 over 10 can be reduced. We can't really do anything else with the root 2, but at least 6 over 10 can be reduced to 3 root 2 over 5. Okay? And there is our final answer. So the denominator has been rationalized, and also it is in lowest terms. So I'm going to let you summarize how do you rationalize the denominator. Do that yourself in that space that you have provided. Let's try another question that's a little bit more complicated. 2 over 2 root 5 plus 3. If we try our same strategy here, what's going to happen? So our strategy said, let's multiply by whatever the irrational number is, the root 5. Let's multiply the numerator and the denominator by that and see what happens. Root 5 over root 5. So let's try simplifying this. 2 root 5 in the numerator and the denominator, we have to distribute that root 5 to both terms, right? So we're going to end up with the 2 root 5 times root 5, which is going to give us 2 root 25, and then plus 3 root 5. And then we can simplify that. Can't simplify the numerator, 2 root 5. The denominator, though, 2 root 25. Root 25 is just equal to 5, so 2 times 5 is 10, plus 3 root 5. Can we simplify that anymore? Not really. And we still have an irrational number in the denominator. We still have that root 5. So we haven't really solved anything here. And we could actually keep on doing this over and over and over again, multiplying by root 5 over root 5, and we'll never get a rational number in the denominator. So we need another strategy here. This one just doesn't work. So starting from scratch, what we're going to do is we're going to do a little trick that involves multiplying not by just root 5, but we take the denominator and we're going to multiply by the opposite sign. So for example, 2 root 5, instead of plus 3, I'm going to multiply it by 2 root 5 minus 3. And I'm going to do the same thing in the numerator, because I have to do the same thing in the numerator and the denominator. And let's just see what happens here before we ask too many questions about what's going on. So I got to distribute in the numerator, I got to distribute that 2 to both terms. So 2 times 2 root 5 is just 4 root 5. 2 times negative 3 is negative 6. In the denominator, I have 2 root 5 times 2 root 5. And what that's going to give me is 4 root 25. And then I have 2 root 5 times negative 3, which is negative 6 root 5. And then I have 3 times 2 root 5, which is 6 root 5. And then lastly, I have 3 times negative 3, which is going to be minus 9. Now we can simplify a little bit more. Can't simplify the numerator anymore, so that's still 4 root 5 minus 6. But the denominator, look what happened. So we have, first of all, we have the 4 root 25. Root 25 is just 5, so 4 times 5 is 20. But look what happens to those two next terms. Negative 6 root 5 plus 6 root 5. See how those are opposite signs? That means they're going to 0, right? They're going to sum to 0. And then we have a minus 9 at the end. Ooh, that's looking a little bit better. So in the numerator, we have 4 root 5 minus 6. In the denominator, we have 20 minus 9, which is just 11. Look, our denominator has been rationalized. So this little trick, if we go back to the beginning here, the little trick to multiply by the thing with the opposite sign in the middle, that's called using the conjugate. This thing right here is called the conjugate. Conjugate. And it is conjugate to 2 root 5 plus 3. So the conjugate is just the thing with the opposite sign. Think about why this works. It actually always works when you have these multiple terms in the denominator. I want you to think about why it works. So let's try the next question. 7 root 2 over root 16 plus root 12. What do you think we're going to multiply the numerator and the denominator by? Well, the answer is the conjugate. And the conjugate this time, we just have to change the signs, right? So it's just going to be, instead of root 16 plus 12, root 12, it's going to be root 16 minus root 12. And then we have to do the same thing to the numerator, root 16 minus root 12. Okay, let's just distribute, collect like terms, simplify, all that jazz. So 7 root 2 times root 16 is going to be, oh, I can't do this in my head, 7 root 32 minus 7 root 24. In the denominator, 16 times 16, well, I know 16 times 16 is going to be whatever number it is, but then when I take the square root of it, it's just going to be 16, right? And then 16 times root 16 times root 12, that's going to be, I don't even know what that is, but I'm just going to put negative root 16 times 12, like that. Then I'm going to do plus root 12 times 16, like that. And then the last two terms, it's going to be root 12 times negative root 12. And again, 12 times 12 is 144. The square root of that is just going to be 12. So I'm just going to end up with minus 12 here. Look at those two middle terms again. Look what happens. We have root 16 times 12 and root 12 times 16. Those are the same things, opposite signs, so they're going to cancel out. And then we can just simplify our numerator. So we have our denominator, 7 root 32 minus 7 root 24. And that is all over 16 minus 12. And 16 minus 12 is 4. There you go. Is our denominator rationalized? Yes, it is. All right. So what I want you to do now is I want you to summarize how you rationalize an expression such as root a plus b. And the key word here is conjugate. So do that yourself. And then try example 3, a and b. Pause it here, give those two a shot, and then when you're ready, unpause it and I will show you the full solutions. So here are the solutions to both of these questions. The first one has a nice answer where the 6 goes into both terms in the numerator. But in the second one, B, you see the answer is quite ugly, but it is rationalized. So that is the case. Now, if you want to check your answers here, the easiest way to do it is plug in that first term, the question, into your calculator, and plug in the last term into your calculator, and check to see if they come out to the same number. And this is just a way of making sure you didn't make any algebraic errors. So I did this here, and if you plug in the first term, you should get about 0.605 from your calculator. So this is about equal to 0.605-ish. And the last term, if you plug that into your calculator, you should get the same thing, which you do, 0.605. So that means we didn't make any algebraic errors, and it is rationalized.